Okay, good afternoon, everybody. My name is Ioannis Bakas. From those who remember me from the previous lectures in July and September, I'm going to talk about more technical issues. And we are now entering the core of Module 5. Module 5 is focusing on the propulsion and power generation of LNG-driven vessels. This means that we need to make a more detailed analysis on engines running on LNG, either as pure fuel or as dual fuel. My presentation, my lecture, let's say, is focusing on the main principles. And this is due to the fact that tomorrow and the day after tomorrow, we are going to have dedicated sessions by specialists. Tomorrow, Varchila is going to deliver a full-day lecture regarding their engines and their approach on LNG solutions. And the day after tomorrow, the same will be done by MAN. So today, only some introduction for you to know what it's all about. And of course, more details to follow tomorrow. The contents of this lecture are 6. You may see them right now. We are talking about lecture introduction to LNG as marine fuel, introduction to marine engines running on LNG, some approach on safety classification and operational issues, where we are standing now regarding research and development, what are the challenges, and some conclusions and food for thought for tomorrow and the day after tomorrow. Let's start with the lecture introduction. The purpose of this lecture is to highlight some principles on marine engines running on LNG, either as pure fuel or as dual fuel engines. Everybody knows that during the last few years, the gas-fueled engines are now somehow popular in the marine industry as well. The applications were started almost 30 years ago, mainly in land-based infrastructures like power plant generators. But now the marine industry is getting the lead as well, and we are using the LNG fueled engines for onboard generation, power generation and propulsion duties. Initially, in the maritime sector, the LNG engines were used in the pure LNG tankers, and this was based on the fact that the LNG tanker was able to use the cargo itself, portion of the cargo, of the LNG cargo, in order to burn more efficient and clear fuel. In the recent years, we do have to comply with strict emission limits. For example, SECA areas are now being established in the Northern Europe, and they are going to be established in the Mediterranean as well. This means that we need to control the limits, the emission limits of NOx and SOx, and this can be done with the LNG. The LNG is now becoming more attractive, not only for environmental reasons, but also for economical reasons. We are now facing reduced prices in LNG as fuel. A very brief introduction in LNG. I'm not going to repeat the basics of LNG that were presented in the previous lectures and also was presented today by Ms. Damianidou. I'm going to focus on what is LNG, how LNG is performing, let's say, within the engine cycle, and how the LNG is to be used as marine fuel. Everybody knows that LNG stands for liquefied natural gas. It's a natural gas that is cooled down to minus 163 degrees approximately at an atmospheric pressure, and it is transported as a liquid in order to achieve economy of scale and easiness to transport the amount of the LNG. As we already said, it is now rapidly becoming a widely used engine fuel in association with its growing popularity as an energy source worldwide. Let's now discuss about LNG on board. We assume that everybody is familiar with how the LNG is being produced in the refineries and how it is being transported. And then now, whatever I'm going to say stands from the point that LNG is on board the vessel and it is ready to be directed to the engine. So, there are two distinct ways of gas made from LNG depending on how it is extracted from the tanks. We have the natural boil-off gas and we have the forced boil-off gas. The natural boil-off gas means that we are taking off the top of the LNG tanks above the liquid, and this gas is to be used as a burning fuel. This particular part of the LNG cargo within the LNG tanks has a high methane content and of course some nitrogen particles, and this gives a very high knocking resistance. For those who are not familiar with knocking resistance in a fuel, the explanation is that the knocking resistance is the point where the fuel can deliver the thermal power. Apart from knocking resistance point, the fuel cannot deliver any thermal capacity, and it is burnt out, it's useless. Our analysis shows that typical values of methane number is close to 100, which is a very high methane number for the boil-off gas. And the low calorific value, the LCV, stands between 33 and 35 megajoule per nanocubic meter. And this is a very good value from a thermal point of view for the LNG to be burned within the combustion chamber of the engine. The natural boil-off gas is the main application to be used on LNG tanker propulsion plants. We are referring to tankers that they are carrying the LNG. The forced boil-off gas is another method, and within this method we are using LNG that is extracted from the down of the tanks, and it is evaporated separately in the so-called cold box. This gas contains a mixture of all hydrocarbons in the liquid, and the resistance in knocking may differ from origin to origin, depends on the nature of the LNG, and even from load to load from the same source. The MN, the methane number, typically is lower and revolves in the range between 70 to 80. The calorific value will be higher than natural boil-off gas, and it is quite stable at around 38 to 39 megajoule per nanocubic meter. And this is now the standard gas type to be used in the maritime shipping and in the engines burning LNG. The knocking stability of the LNG as marine fuel, as we said, the natural boil-off gas from the top of the tanks is very high in methane and has good knocking stability. It is therefore particularly well suited as an engine fuel. However, when a propulsion system is let out for the use of this type of gas, it is important to ensure that there is always enough natural boil-off gas with sufficient high methane content available, so that there shouldn't be any need for mixing in forced boil-off gas from the bottom of the tanks. What does it mean? It means that in order to use boil-off gas, we need to have large capacities of this type of gas in order to avoid mixing with the liquid form of the gas. This is the reason why we are using this method to large LNG tankers, that they are carrying huge amounts of LNG, and they do have plenty of boil-off gas quantities to be burned in their engines. Engine installations that they are specifically designed to be fueled by LNG should preferably use the forced boil-off type, with the LNG taken from the deep down in the tanks and then well mixed before extraction into the evaporator. This methodology will ensure good homogeneity of the LNG taking out and hence constant gas quality. One point of importance is that we should be aware that this type of LNG-based fuel tank will be different from the natural boil-off from the tank top, and the rating of the engine will have to be based on a somewhat lower MN in this case. in order to ensure, of course, smoking-free operation. It is of vital importance to size the proper evaporator correctly, and the evaporator should be sufficiently large in order to ensure that no gas droplets are entering the engine even under severe transient conditions. As a bottom line, we should remember that the forced boil-off type of LNG does not produce the same power to the engine as a bottom line like the natural boil-off gas. Now, let's go to the core of this lecture, that is the introduction to marine engines running on LNG. First, a few words about the development of the LNG fuel marine engines. As we said before, the development of the LNG fueled marine engine started back in early 80s in order to develop engines that they were on board LNG carriers and they were utilizing boil-off gas as a fuel. The opportunity was reviewed in the late 70s, where a large amount of LNG were transported, and somebody thought, why not start using LNG, at least the gas part of the LNG from the huge transportation tanks, in order to see if we can sustain the burning ability within the marine engines. This experiment was successful, and then there was a steady commercial engine development that started around in 1984, and during the next, let's say, 12 years, up to 1996, we had three proved engine concepts that were released. The first engine concept is the so-called the Otto cycle. It takes the name after the principle that the normal Otto engines are operating, that is spark-ignited lean-burnt engine. The second concept is the combined Otto diesel cycle, and it is called the diesel-ignited dual-fuel engine. And the third concept is the so-called diesel cycle, and it is the high-pressure direct injection engine. We will analyze all three concepts later on in the next parts. The initial field of application of all these three engine concepts were land-based stationary power and heat generation, COGEN, and the first pure marine application was not until 2000 with the prototype LNG fuel ship being the car ferry Glutra. It's, if I remember correctly, a Norwegian car ferry, small car ferry, operating the coastlines of Norway. In 2003, the commercial market of this LNG sector started growing from the small-scale LNG project. And the small-scale LNG project is all actions referring to how to transport and distribute LNG in smaller quantities, not the big ship application, but smaller volumes and smaller cargoes between ports or between ships. In 2011, a fast-growing interest was started regarding the deep-sea shipping applications, and now is the point where we are standing and where we are producing relevant studies on how to incorporate in an efficient way the LNG in the deep-sea shipping. The reasons for this interest are mainly three. The first reason is that we are driven by emission control legislation and fuel cost. The second reason is that we have now large slow-speed engines under development to be used with LNG. And the third reason is that we are now designing new ships, and we are considering retrofit installations on existing vessels in order to burn LNG. Behind all these three reasons, there is one major initiative, that is strict environmental emission controls and better economy of scales to be achieved by using LNG. So let's go into more detail, but again keeping that as an introduction, in an introduction mode, to the types of the marine LNG engines that they were previously identified. As was described, three main types of LNG burning engines are available to the marine industry, which are coming out from different development directions and hence with some different characteristics. The first type is the spark-ignited LNG-only engines that were first developed for the land-based power industry, and they do have major, this industry has major requirements, but also needs simplicity and good overall performance at lowest total emissions. These engines are dependent on permanent gas supply and initially came into the marine industry as engines for short distance ferries. The spark-ignited LNG-only engine should be applied, as it is said, only with LNG. We cannot use it with any other type of fuel. The diesel-ignited gas engine with dual fuel capability was also originally developed for land power plants, and it has an ability to operate both on liquid and gaseous fuels at high specific power, and this is a particular advantage. Sorry? Speaking. Ερώτηση. Έχει ερώτηση. Okay. So I think we can continue with description of the three types of marine LNG engines. We described the spark ignited LNG on the engine, and we are talking about the diesel ignited gas engine. This particular engine has a dual fuel capability. Initially, it was also developed for land power plant use, where its ability to operate both on liquid and gaseous fuels at high specific power was a particular advantage. Development was originally focused on low NOx emissions at high load recently. However, a focus is also on part load performance and variable speed capability. The diesel ignited LNG engine is the first type to establish itself in the maritime industry and is currently the dominating engine type in this market. The direct gas injection diesel gas engine is the third type of marine LNG engine, and initially came to use in the offshore industry, where its high flexibility and very high power density is of prime importance and prime attraction. The concept is unique, imposing no particular requirements to the self-ignition stability of the fuel gas, and its diesel operating principle ensures that the combustion of the gas fuel is very complete. However, there is a cost, and the cost is we have higher NOx emissions than other gas engines, and to this aim we need to take other measures in order to minimize the NOx emissions. Currently, the use in the maritime sector is still limited, but it is promising because the R&D development is rapidly growing towards a more stable solution. The gas burning engines, regarding the principles, we having two different principles, as we stated, the premixed auto and direct injected diesel cycles. The auto gas engines, we have the gas only spark ignited engine and the diesel ignited gas engine. For the first one, we are using either the typical well-known carburetor, or we are using port injection of gas. Those are single fuel engines, and therefore they must meet some special redundancy requirements in order to be used on board vessels for marine applications in principle. The diesel ignited gas engines, that they have conventional low pressure gas feed as above, they do have an ignition principle by injecting a certain quantity of diesel fuel, also known as auto dual fuel, or low pressure dual fuel principle. This type of engines will always need a certain quantity of diesel fuel to be burned with the gas in order to run in the gas mode. On the other hand, they may also run on 100% liquid fuel, either diesel or heavy fuel oil, that is a dual fuel capability engine. So please bear in mind that when we are talking about spark ignited engines, we are talking about gas only, and when we are talking about diesel ignited engines, we are talking about dual fuel engines. Both of these engines are using the auto principle. That is, we need a sparking source. In the first type of the engine, the gas-only engines, the spark is a typical spark. In the diesel-ignited engines, the role of the spark is being played by a small amount of diesel that it is sprayed within the combustion chamber together with the gas. I will show you some pictures later on in order to understand the principles. The auto gas engines presenting this homogeneous combustion, they generally display low NOx emissions and a high efficiency rate. and they typically comply with the IMO Tier 3 limits, which are very strict limits regarding emissions, without any need for exhaust after treatment. The con of these type of engines is that they require a certain stability of the fuel gas against self-ignition, and they must be carefully developed in order to keep unburnt gas, that is the methane slip, so-called methane slip, to a minimum point. The spark-ignited and diesel-ignited gas engines show some differences, especially at part load. We consider the spark-ignited that the spark-ignited engines they cannot display a part load capability to the same amount that the diesel-ignited gas engines can display. The diesel gas engine is the engine where the gas is directly injected at high pressure into the cylinder after the diesel pilot fuel has ignited. We are calling this type of engine as a diesel because in principle it follows the diesel burning principle. That is, we spray fuel directly in the combustion chamber without any further spark ignition source. This is also known as the diesel dual fuel principle, or the gas direct principle, and such engines also have dual fuel capability and may also run on 100% on liquid fuel, either diesel or heavy fuel oil. The diesel gas engines, they have a diffusion burning which ensures good capability of burning gases with low Newton stability, that is a low methane number, and at the same time they are producing low emissions, methane slip. We are avoiding the methane slip. However, this type of engines, they do require a high pressure gas system, typically in the range of 250 to 300 bar, and we also need additional exhaust after treatment in order to comply with IMO Tier 3 NOx emission limits. So, on one hand, we have a simpler methodology of burning the fuel. On the other hand, we need to establish on board a high-pressure LNG system that can treat the fuel before entering the engine. And also, we need to take other measures in order to comply with IMO Tier 3 emission limits. Some pictures now for you to get what has been described in a visual way. Starting with a spark-ignited lean burn gas engine. Just for reminder, this is an LNG only use engine. No other fuel can be used on this type of engine. We are using low pressure gas supply in the region of 4 to 5 bar, no more. This engine can display a higher efficiency at high load, higher than the corresponding diesel type of engine, but the ability to take partial loads is lower than the other type of engines. We do have low emissions that they can meet the Tier 3, IMO Tier 3. They are very sensitive to gas quality. We need gas with a high methane number, and we need a constant supply of this gas. Otherwise, the engine may present some hiccups in operation. This type of engine is not suitable for retrofitting of any existing engines. We are talking only by new engines. We are not talking about retrofitting engines with this type of gas burning principle. And a typical oil engine example is that the engine that you see is a Rolls-Royce C26 33L9. To the right you can see how the burning principle operates within the combustion chamber of the engine. We have a jet of gas sprayed inside the compressed air of the piston area, and we have a spark plug that produces a flame within the rich zone, and then we have ignition. Of course, we are talking about lean burn gas. This means that we need to establish a high ratio of air, atmospheric air and gas. The second type of Otto principle engine is the diesel-ignited dual-fuel engine. In this particular engine, as already stated, we have a dual-fuel capability, LNG and any type of diesel fuel. We have again a low gas pressure supply between 4 to 5 bars. This engine also presents a high energy efficiency at high load, and on top of that, it can display a better ability to undertake partial loads than the LNG only fuel engine, the spark type of engine. It can meet the IMO Tier 3 emissions. There's a flexibility in fuel mix. We can, let's say, design the engine with a design point according to our needs. We have no strict limitations on that. It is also sensitive to gas quality, to methane number, but not that sensitive as the previous type of engine. It is a good opportunity and a good selection to retrofit existing engines with this principle, but please bear in mind that this displays an excessive rebuild of the engine, and this will be explained better tomorrow and the day after tomorrow by Wärtsilä and MAN. A typical engine example is the engine that you see is the Wärtsilä 6L50 dual fuel. To the right, you can see the operation principle. You can see that gas, the green dots, is entering the combustion chamber through the inlet valve. The outlet valve is closed. Then the inlet valve is also closed. We have compression. And then we have this red line that you see is fuel that it is spread within the gas that is being already compressed. For those two types of engines, just for the sake of clarification, I repeat that these type of engines are described as Otto cycle engines. That is for the lean burn combustion and the dual fuel. You can see a typical burning diagram where in the horizontal axis we have the air-fuel ratio, and in the vertical axis we have the mean different effective pressure, the thermal efficiency, and the NOx emissions. You can see that we can select the design point as the optimum performance for all cylinders, well away from the knocking and the misfiring area of the fuel, and within the operating window we can achieve very low NOx emissions, almost very close to insignificant amounts. A typical air-fuel ratio for this type of engine stands between 2.1 and 2.3. And you can see that the efficiency is well within the operating window, well situated within the operating window. The other type of engine is the diesel gas injection. The diesel gas injection is of a high pressure engine. It uses the diesel principle, and in this case we don't have any sparkle source. We using gas in high pressure. That is, we are using gas between 250 to 300 or even to 350 bar, depending on the manufacturer. We can use this type of burning in both 4-stroke and 2-stroke engines. We can also have a multi-fuel capability, LNG and other type of marine fuel engines. However, we cannot meet the IMO Tier 3 emissions. That's why we need additional reduction techniques regarding NOx emissions. This type of engine is not very sensitive to gas quality. We can use an LNG that has a lower methane number than the previous engines. We do need on board separate and dedicated installations in order to pump and compress the LNG to 350 bar and evaporate it in these conditions. It's not a big deal, it's a simple process. However, we do need a dedicated area on board the vessel, and this should be taken into consideration while designing such systems. This engine has also flexibility in fuel mix, and we are talking about retrofitting existing engines with this principle, and the retrofitting is of more simpler conversion than the diesel ignition engine, and this is also attractive for the deep sea shipping. Just to come back to what has been described before, the deep shipping industry, marine industry, is now starting to looking at LNG applications, and taking into account that the majority of the deep sea vessels are using two-stroke engines. This type of LNG burnt engine seems quite attractive to the ship owners. A typical example of this type of engine is a big engine of MAN diesel, for example, Megi models G40 to G95. For the records, the G95 is a huge engine, specially designed for very large crude carriers, and develops very high power from a single engine. More details will be displayed by MAN during their dedicated presentation. In these slides, I have gathered all three different operated engines in one picture for your convenience. Let's start with the Lindburn spark ignited engine. Again, it is LNG only, and it works like the typical gas engine in our cars. The gas is entered in the combustion chamber, the piston is compressing the gas, and then we have an ignition source in the form of a sparkle, and then we have ignition, and the cycle continues with the piston and the gas exhaust. The dual fuel gas engine, that is again operating under Otto principle, is a little bit different. We have again the entrance of the gas in the chamber. We have the compression of the gas, and during the compression to the upper limit point, for those that they know the mechanical principles, we have injection of fuel, and the role of sparkle is being played by the fuel, the normal fuel, and then we have ignition of the gas. The third type of engine, the pure diesel engine, is of high pressure gas injection. That is, we inject gas in a very high pressure, and we are burning it the typical way. Everything is being burned, everything in the fuel is being burned within the two-cycle engines. So, after finishing this, and just to repeat, and I'm sorry to repeat it again, but I want to make it quite clear, this was just an introduction to the methodology and the design and the types of the marine engine available for running on LNG. We are going to have 2 full days with the major engine manufacturers, Wärtsilä and MAN, and they will address every single point regarding the technology of this engine. So this was just an introduction for you to have an initial picture, and in order for you to be able to follow tomorrow and the day after tomorrow what is going on. Let's go now to some safety, classification and operational issues that are evolving around the engines. Classification issues. Of course, as you may understand, this is a very large topic, and we can make only some general statements in this lecture. First of all, let's see what IMO is doing, because IMO is formulating the principles that we are going to revolve around regarding the LNG. IMO has developed the IGF, the International Gas Fuel Code, the IGF, which is based on the interim guideline MSC 285 of 2009. The latest news, not the breaking, the latest news is that IMO finally concluded on the final draft that has been released in June this year, and it is expected to come in full force in January 2017, in a year from now, more or less. IGF is a standalone code, is not a part, let's say, of SOLAS or of any other legislation, and this code addresses all technical issues regarding the use of LNG on board as fuel, not as cargo. This is very important for you to clarify. IGF deals with LNG as fuel and not as LNG as cargo. Besides the IGF, the majority of the internationally recognized classification societies have issued their specific sets of rules regarding LNG to be used as a marine fuel, and these guidelines are either already applicable or are out as preliminary drafts. And of course, I'm referring to the 5 IACS member classification societies, and which are monitoring the majority of the marine shipping industry. The dominating philosophies of all legislation currently out or soon to be out is revolving around how to avoid the danger of explosion, how to maintain the ship operational. I mean, what is going to happen in case of loss of power, in case of shutdown of the gas supply, and how are we going to demonstrate the ability to take actions regarding emergencies. Safety issues. Again, we have a lot of points for discussion here. The IGF and the Classification Society's guidelines are addressing all the issues at the moment, applicable at the moment. And from my experience, I can tell you that we are adding constantly new points for further consideration regarding safety and regarding proper design. However, if we are focused now on the engine room itself, and let's say that we don't care for the moment regarding the other LNG applications on board, if we are going to limit our interest in the engine room, when we are designing the engine room for a dual fuel installation, we need to take care about a couple of issues. The first of this issue is how to prevent any kind of explosion. In order to establish an explosion prevention, we are using 2 main options. Either we should have a double-wall gas feed piping to the engines, and this type of piping should be provided with venting of the space between the inner and outer pipe walls to a gas detection system in order to be alarmed in case of leakage, or to place the engines in a separate gas-tight and ventilated engine rooms, which each has its own gas supply, required number of air exchange per hour, is well protected with gas sensors, and has a required pressure relief and escape ducting, and all the other measurements already addressed in the IGF or in the class society's guidelines. The first application, that is to establish a double-wall gas feed piping to the main engine, is the most attractive solution in case of retrofittings. As you may well understand, it wouldn't be easy within the existing engine room to install and to create totally separated engine rooms. That's why we are using the ventilated double wall piping as it is in the sketch that you see. The second option to place the engines in a separate gas-tight and ventilated engine rooms is more applicable to new builds, where we have the flexibility to design the engine room from scratch, from white paper, and we can adopt this design. A second point regarding safety issues is, of course, to use electrical equipment categorized as X-proof for obvious reasons, to design a dedicated ventilation system just for the LNG installation, equipped with a separate emergency relief system, and this ventilation system must be truly dedicated to LNG and must not come in connection with any other ventilating system on board the vessel. We need to design the LNG bunker station according to IGF and class rules. There are certain requirements about this area now, from the required floor area that we need to have, up to ventilation, fire protection, airlock accessibility, etc. Of course, we need to either to reinforce or to create additional firefighting and life-saving measures on board regarding the areas where the LNG is being used as a storing facility or as the LNG piping system that runs within the spaces. And of course, we need to have dedicated escape ways from any LNG designated area, preferably in opposite directions. And last but not least, and this deals also mainly with operation, we need to establish and to monitor the safety zone during LNG bunkering operations. Operating wise, the engine that runs on LNG must meet all relevant class and other IGF, for example, rules regarding the design. Now, the next point, it's not very well addressed at the moment, but we need to take that into consideration. If we have an engine that runs on LNG as a marine driver, not as a generator, we need to consider the variable speed requirements. And this is also important because of the transient load capability of the gas engine. Because, as you may know, during the operation of the ship, the marine engines are running not constantly on the design point, but they are running also on partial load. And although this is well executed by using the typical fuel, this is still to be addressed while using LNG. LNG does not stand that well at the moment as the fuel regarding partial loads, and so far we have recorded the following capabilities of the three types of engines already addressed. The direct injected gas engine, we have a better transient capability than the mixture charged engine. And this is also a practical advantage in fulfilling the requirements of double-wall gas piping systems for installations in conventional engine rooms. The low-pressure dual-fuel engines are best used in steady, medium, and high-load applications. And the diesel gas engines have part load and transient response characteristics similar to diesel engines, provided that the fuel gas system is capable of handling such variable demand. The bottom line is that all three LNG type of engines are displaying partial load capabilities in a less extent than the typical fuel engine currently in use. And in between those three types of engines, the diesel ignited gas engine presents one might say, the best ability to undertake medium to high load applications. This is an area where the R&D development is focusing on because we need in the very near future engines that they will be stable and capable of undertaking partial loads of the ship, but with higher efficiency as they can do it right now. And speaking about R&D, let's see what the R&D challenges are regarding this type of engines. We have three fields of R&D challenges. The first field is the engine and system itself. As already stated, we have the part load efficiency optimization, which is still to be, let's say, provide a better solution. We have the methane slip reduction, and this is also a headache for the engine manufacturer because we are losing some LNG out of the burning cycle. We have to establish and we have to see how to establish a fuel gas quality, which is essential for these engines. They are very sensitive to quality of the fuel as in principle. And of course, we need to see how to reduce the production cost of the LNG. Regarding the fuel handling and storage, of course, we need to find better storage tank solutions regarding space on board and cost. We need to improve the fuel handling systems, the bunkering logistics in principle, and we need to find out simpler and more robust fuel system design without reducing safety, space and cost. And finally, the commercial challenge is how to create economy of scale regarding LNG. This is a huge topic by itself. We need more actors in the market, and this is out of the reach of this lecture. It's just for presenting the challenge in the commercial part. Finally, some summary and conclusions. The conclusion so far is that LNG is considered to be the most promising alternative marine fuel. Using LNG as fuel, as marine fuel, has some results of very low exhaust emissions. LNG is available worldwide in large scale, and it can be further distributed to small scale fuel market. We can display now proven engine technologies for medium speed natural gas engines and some slow speed two-stroke engines. We are still developing this field. We're pretty sure that we will have very good engines in the very next years regarding two-stroke engines. We have an energy efficiency in theory equal or even better by using LNG. The challenge is to create the engine that it will use this energy efficiency in a better way than marine diesel fuel and heavy fuel. Of course, LNG fueled engines are more environmental friendly and they can meet the strict emission requirements. The engine R&D challenges are well under addressed and are related to part load efficiency and to other issues like methane slip and variable gas composition. Of course, we need to solve the availability of LNG on board regarding storage and handling systems. And last but by no means least, because it is money now that counts, we need to see how the higher capital investment in LNG fuel system can be accommodated and how to display lower operating costs, emission and fuel in order to counterbalance the initial capital investment. This is a case that it will be a huge matter within the next years, but the industry is pretty sure that a solution will be drawn very, very soon. So this is all about. Thank you very much for your attention. The purpose was to display the introductory items on how to use LNG on fuel as a fuel in the engines. And I can promise you a very interesting day tomorrow and the day after tomorrow with specialist Bachelor in the mine. Thank you very much.